Now that we have a couple of initial transformations in our toolbox, let's actually try to approach one common problem that we have, and that is skewness. And we want to think about ways that we can transform our variables in order to reduce skewness. Now, statistical methods such as least squares summarize distributions using means. That's really important. Remember, with linearity, we're assuming that the regression line is going through the conditional means for each value of x. And so if there's a skewed distribution, we're not going to get a very good summary of its central tendency. So unusual values in the opposite direction of the skew can actually hide the true effect. And highly skewed distributions are also really difficult to examine. Now, we can use these power transformations to make a skewed distribution a little bit more symmetric. So we're going to talk about how a power transformation can eliminate a positive skew. Now, let's take this example where our covariate x has values of 1, 10, 100, and 1,000. Now, that's a pretty wide dispersal, and if we have only a couple of values at 1,000, we're going to have a skewed data set. Now, we can take the log of x, and that transforms our covariate into 0, 1, 2, and 3. So as we decrease the ladder of powers to log x, that's going to make the distribution more symmetric by pulling in that right tail. Now, if we increase the ladder of powers toward like x cubed or x squared, that can also correct for a negative skew. So if we have more data higher with few observations lower. And we're going to walk through an example in the next slide. So the example that we're going to be talking about is data that comes from the UN about infant mortality here. And what we can see on the far right is the original variable. And we have a couple of observations that are falling quite far outside the normal distribution of infant mortality. And so there's probably a couple of countries that have really high rates of infant mortality. And what we're doing here is we're seeing how different transformations of our data on infant mortality reduces the skewedness of the distribution. So if we take the log of our covariate, we can see that that really straightens out the distribution and recenters our data. So all this is to say that we have some decisions that need to be made as far as what transformation we want to use in order to correct for skewness. And again, this is really going to come down to how easy it is to interpret the transformation that we make. So with log transformations, we do have a convenient multiplicative interpretation. Now, again, remember, if we have log base 10, if we add 1, we're really multiplying x by 10. And in certain contexts, other transformations have specific substantive meanings. So in physics, right, the inverse of time required to travel a fixed distance is speed, and the square root of a measure of area, like meters squared, is a linear measure of size. Like if we're interested in volume, right, a cube of a linear measure is volume. And what's cool is that power transformations can be used to make many non-linear relationships more linear. And here's an example that we have between an x and a y that is a non-linear relationship, right? Now, we can see with a transformation how to kind of straighten it. And we're going to take the square root of y, and we're going to replace x with x squared. And again, both of those are going to have the same ability to straighten out that non-linear relationship into a linear relationship. So there is basically no difference between the two. We are just using two different transformations to straighten out our nonlinear relationship. And this leads us to kind of a rule of thumb that we can use, which we'll talk about in the next slide. But generally, power transformations are going to work really well when the relationship between your covariate and your outcome is monotonic, in the sense that it's moving in one direction, and simple. Again, it's not changing direction. So this is simple and monotonic, right? It's ever increasing, and it's not, very complicated. This is monotonic in the sense that it is still ever increasing, but there are multiple curvatures or dips in our line. And this is certainly simple, but it is not monotonic in the sense that it is decreasing at certain parts of the function and then increasing. So our general kind of rule of thumb is going to be called the bulging rule, and it's going to make a little bit more sense when I show you this diagram. And so if the nonlinear relationship is bulging down toward this lower quadrant, we may want to take either the square root of our outcome or take a power of our covariate. So just like the example that we had in the previous slide, in which the relationship, again, was going from the origin and going up like that, we took either the square root of our outcome or we squared our covariate to make the relationship more linear. To drive this point home, let's go over an example. So here we can see the relationship between income in dollars and prestige. And this relationship is nonlinear, it's pretty simple, and it's monotonic. What should we do? So we have a couple of different transformations at our disposal. One, we could take a power of prestige and decrease that power. We could increase the power of income. So again, if we decrease the power of prestige, we would be either taking a negative value or the square root. We could also increase the power of prestige. Now, since the bulge points up to the top left, what would we want to do? Now, we would try transforming prestige by increasing its powers or taking maybe the square root of income. And actually, if we take the cube root of income, this transformation actually works pretty well to linearize the relationship between income and prestige.